I'll discuss the work done assembling a group of charges. Now, at the end, I'll give you a formula for arbitrary number of charges, but let's start with 3 charges. I have them at infinity. They're just waiting there to be called. So let's take the first charge and bring it from infinity to some point. It really doesn't matter in what path you choose, because potential energy in electrostatics is conservative. So let's bring it to some point A. Now the potential at point A before I brought the charge in was 0, and the potential at infinity is also 0. So the total work done bringing the charge Q1 in, which I'll call W1, is just going to be Q1 times the change in voltage, which is the final voltage minus the initial voltage. And so that's going to be Q1 times 0 minus 0, or 0 joules. So there's no work done. The first charge is free. Now, having brought the first charge, it is going to set up a electric field around it, an influence. Assuming it to be positive, if you try to bring any other positive charge near it, you will have to do work to bring it closer and closer because it wants to repel. And that concept is encapsulated in the potential energy concept. So let's assume that into this neighborhood, you want to bring a new charge in at location B. That charge is Q2. Now, when you try to bring the charge Q2, like I said, there are 2 possibilities. If they are the same sign, you'll have to push it in order for it to get closer. If they're the opposite sign, you have to keep it from accelerating. So you have to apply the work in the opposite direction. In either case, the work done is given by the same type of formula. The work done to transport the charge Q2 is going to be Q2 times the potential at B minus the potential at infinity. Now the potential at B is not 0 because charge Q1 will create a potential at B. So let's put a distance here. Let's call this distance R12 because Q2 is going to end up there. So 1 and 2 refer to the subscripts in charge Q1 and Q2. So I'll get Q2 times the potential exerted by Q1. We're going to use the point charge formula, and that's going to be KQ1 divided by the distance R12 minus V infinity, which is still 0. So I'm going to get K times Q1 Q2 divided by R12. Now observe this interesting structure. The subscripts 1, 2 appear above and below. Let's finally bring the third charge in. The third charge is now going to have to deal with these 2. So they're both going to start sending out influences, and the third charge will have a even harder time getting in place. So let's suppose we want to put the third charge at some location here. We'll call that point C. And I'm going to put similar distances. So since Q3 is going to end up there, we're going to put a distance of R13 here, and we're going to put a distance of R23. So those are the distances from the previous occupants of this neighborhood. Now the work done is given by the same formulas. So it's the charge in question, and that's the potential at C minus the potential at infinity. Well, the potential at C is now being created by both A and B. They're both putting out some potential there. So I have to take that into account. So V sub C is due to charge Q1, I'm going to have KQ1 over R13 plus due to charge Q2, I'm going to have KQ2 over R23. So let's write this out. I get KQ1 Q3 divided by R13 plus K Q2 Q3 divided by R23. You can see this really interesting structure developing. The subscripts in the numerator and the denominator are the same in all these cases. The net work done assembling the configuration is given by the sum of all these things, sigma wi. And so that's going to be 0 plus that plus that. I'm not going to write 0, but I'm going to get k times Q1 Q2 over R12 plus k times Q2 Q3 over R23 plus k times Q1 Q3 over R13. Now there is a compact way to write this using the summation sign, and that is the following. I'm going to write this as sum I less than j kqi qj divided by rij. Now it's understood that I goes from 1 to 3. Now all I have to do to take this formula to an arbitrary number of charges is to put n there. So for n charges, I have the work done is equal to the sum I less than j equal to 1 kqi qj divided by rij. Now some authors, textbook people, don't like to have this I less than j business. So they write it as 1/2 the free sum over I and j going from 1 to n of kqi qj over rij. By the free sum, I mean they allow things like R12, R21, R13, R31, R23, R32. In other words, each term is counted twice because there is no restriction that the first index be smaller than the second index. In here, we are restricting that the I is always less than j. That means you can only have 1, 2, 2, 3, and 1, 3. You can't have any other terms. If you remove that restriction, you can have 1, 2, 2, 1, 2, 3, 3, 2, 1, 3, and 3, 1. So you have to divide by 2 because you're double counting the terms. Either of these two can be used. Now, what is the change in potential energy of the system as a result of your work? Now, from basic ideas in UP1, we know that the work done by the field is negative the change in the potential energy. But the work done by the agent, that is in this case me, I'm the one who is playing God, bringing the charges from infinity, is going to be plus delta U. So whatever I do increases the potential energy because I'm working against the field. So this expression here is also, either of these two expressions, also describes the electrostatic potential energy change in this process. Now actually, the change in this process is the potential energy itself because the change refers to final minus initial. Well, the final potential energy is whatever you have here. The initial potential energy at infinity is 0. So this delta UE is in fact the potential energy of the system itself. So I'll have here the final expression for the potential energy of a n-charge configuration. It's I less than j equal to 1 to n of kqi qj over rij. Or equivalently, it's 1/2 the free sum kqi qj over rij.